Let's now get back. We ended last class and we just started talking about UV vis spectroscopy. We talked about conjugation and how when we get more and more conjugation, that energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital gets smaller and smaller, and we have these electronic transitions which we can probe using light, and we get electronic transitions. So for hydrogen gas, it's a very large energy gap, and we have to use pretty energetic light, UV light of about 100, not about, exactly 111 nanometers. Now if we used 112 or 109 nanometer light, this transition won't occur. You have to put the exact amount of energy in to promote one of those electrons from the HOMO to the LUMO. Okay? And we saw that now we looked at the pi star, considerably lower energy light required to make that transition, and as we go to more and more conjugation, that gets lower and lower. We talked a little bit about ketones, and ketones, because they actually have these electrons in these n orbitals or non-bonding orbitals, and that's the lone pair of electrons that we draw on the oxygen. These are higher in energy than the molecular orbitals, the bonding orbitals. They're non-bonding orbitals, and they're closer in energy to the unoccupied orbitals. So we can use very low energy light for those transitions. These transitions, when we look at an absorption spectrum, these things are not allowed, and it's for symmetry reasons. Those of you who are chemists will get into that when you start talking about quantum. We won't worry about it here. I also then told you that we've kind of a little bit misled you with water and with other things when we talk about those lone pair of electrons being energetically equivalent. They're actually not. Their orbitals are slightly different in energy, and it has to do with quantum mechanics. And again, we won't get into that. Those of you, how many people are chemistry majors, by the way? Hands. Okay, quite a few. Good. We're actually going to be seeing some things that you'll see much more of in upper organic level courses. So this just kind of shows you that that gap gets smaller and smaller, and we have to remember when we have odd numbers of p orbitals in a conjugated system, we have a non-bonding orbital. When we have an even number of p orbitals that we combine to make our molecular orbitals, we don't have a non-bonding orbital. We can probe these things using a UV vis spectrometer. That is, we can look at the absorption spectra by putting whatever we're interested in a sample, and we put light through it, and we look at how much light is absorbed at different wavelengths. So we can scan using a monochromator. We have a source that puts out all wavelengths in the UV visible region, and then we select using a monochromator just a very narrow band of that wavelength region and let that through. We let some of it go through the sample. We let another amount go through the same solvent system but with no sample in it, and we compare the amount of light that gets through, the transmitted light, and we can use that, capture it in a computer to build up what we call an absorption spectrum. Those of you that are in analytical, you know this already. For those of you who are chemists taking analytical chemistry, you know about UV vis spectrometry. I want you to remember way back in first year when we talked about atomic electronic transitions, and we talked about emission spectra, but you can do absorption experiments with atoms as well, and you get very sharp absorptions. That's not the case for molecular systems. You get very broad absorptions for molecular systems. And the reason is, here, this is just showing kind of the electronic transitions that can occur from the ground state, and this indicates what the ground state looks like depending on the internuclear separation. This is for a diatomic system. It gets much more complicated for multi-atomic systems, but within that internuclear separation, we have different vibrational energy levels and then different rotational energy levels. So our species can be in a particular electronic state, and it can also be within a particular vibrational and a particular rotational state. As it turns out, most of the time in the ground state, when a molecule's in the ground state, it'll be way down here at the bottom electronically, and then it may be in slightly different vibrational rotational states because of the amount of energy that's in it. When we do an electronic transition, it can go to any of the allowed places up there, and it may go to different rotational and vibrational levels up there. So instead of having what we might expect as being sharp spectrum, we get very broad spectra for molecular systems, for multi-atomic molecular systems. And this is showing the UV vis for carotene, beta-carotene, and lycopene. Lycopene is found in a lot of fruits and vegetables. We talk about it giving the red color in tomatoes, and if we look, we see that it absorbs all this light. And if we look out here, this is the red region beyond 600. It's not absorbing beyond 600. So what's actually going on is that when light hits the tomato, a lot of the light is absorbed, but red light is not. Red light is reflected off of the tomato, and that's why we see a tomato as being red. I know most of you knew that, but it's nice to remind things. Now, if we think about, when we spill some tomatoes on our clothes, we put it in the wash, when that red color goes away. One of the reasons is when we wash it, we probably don't use ozone, but we use other oxidants. We break up that extended conjugated system, and it no longer absorbs light. And then in the wash, we break up more. We actually make it more water soluble, and it goes away down the drain. That's how our wash works. Ketones have available to them both n-pi star transitions and pi star transitions, so we tend to see those. Here's an example of an absorption spectra. This is the compound, and we see down here, we see this. This is due to n-pi star transitions. It's longer wavelength, lower energy light that gets absorbed. This is due to pi star transitions. We have all of these other transitions available as well. Some of them are allowed. If they're allowed, they'll be very strong absorptions. Some of them are not allowed, and it's kind of like when you were kids. There's things you weren't allowed to do, but you did them anyway. So there's transitions that aren't allowed to happen, but they happen anyway, and they tend to be lower absorbing. The UV vis spectrum, energetically, if we take a look, here's the amount of energy in a mole of photons. And when we find in the visible, we're just getting at the energy levels 100 kcals per mole or so. That's actually enough to start breaking chemical bonds. So we can use visible. Actually, we typically need stuff near the UV. Blue light can break chemical bonds, and when we get into the UV, we can use light to break bonds. We're not going to get into that, but I just wanted to mention it. So now, let's talk about some chemistry. Does conjugation affect chemistry? These are all, not all of them. You guys have studied these reactions, most of them 2513, different reactions that alkenes can undergo. So let's take a look and see, do these reactions, do conjugated systems react in a similar fashion? So one of the things, do they behave similar to non-conjugated alkenes? Let's think about those reactions that go through carbocation intermediates. We had a lot of carbocation chemistry that we did with alkenes in 2513. Here is, recall the addition of HBr to alkenes. What happens? It follows Markovnikovs Rule, and that is that the proton adds to the least substituted carbon atom. So here, we're going to add HBr across the system. The hydrogen is going to go to the least substituted, and the bromine, or the bromide actually, because it's actually a proton and bromide, is going to go to the most substituted. And we justified that. Markovnikov found this. He didn't know why. He just noticed that that's what happened. Later, what happens is we form a carbocation by protonating the system, the pi system, and it breaks down. We put the proton there. We get this carbocation, and we form the more stable carbocation always when we protonate an alkene. And this forms a tertiary carbocation. So then it collapses, the bromide just attacks the tertiary carbocation, and that's why we get Markovnikov addition. So we've already seen we can get what we call 1,2 and 1,4 addition in conjugated systems, in conjugated dienes. So we're going to protonate this, and we're going to protonate it. We're not going to the proton's not going to go there because that would make a primary carbocation, which would be very unstable. But if the proton goes there, it makes an allylic cation, which is stable. That allylic cation can have resonance, and we can get what we call 1,2 addition and 1,4 addition. Notice I have this little paragraph. Don't confuse this numbering with nomenclature. We're using it only for purposes of where the atoms go. When we talk about 1,2 addition, the proton goes in the 1 position, and the bromide ends up in the 2 position. If we have 1,4 addition, the proton goes in the 1 position, and the bromide goes in the 4 position. So we have a better understanding of localization, of carbocation stability. We can actually justify this by taking a look. We protonate our diene. We protonate at the end to form an allylic carbocation, and that carbocation has a resonance structure, and our charge is shared between the 2 and the 4 positions of this thing. So when the bromine goes, it can attack either the 2 or the 4 position. So it can attack the 2 position, and we get 1,2 addition, or it can attack the 4 position, and we get 1,4 addition. As it turns out, this is a more substituted alkene. Remember, more substituted alkenes are more stable than less substituted alkenes, and trans alkenes are more stable than cis alkenes. So this is the thermodynamically favored product. Okay? Another thing I want to remind you, these are resonance structures. So this thing is not an equilibrium arrow, it's resonance. The real structure is kind of shared. The positive charge is shared between the 2 and the 4 position there. So that explains our product distribution. But let's take a look now. Let's take a look at some experimental results. If we do this reaction at 40 degrees, we get a distribution of products. We get the 1,2 addition and the 1,4 addition. And the 1,4 addition seems to be favored. However, if we do the same reaction at very low temperatures, by the way, do you think we have water as a solvent in this reaction? Probably not, right? We wouldn't be able to do much at -80 in water. It's probably done in something like dichloromethane, something that's polar enough that we can get carbocation chemistry going on. So we do the addition at -80 degrees, and we get a completely different distribution of the products. What is going on here? So let's take a look. Interestingly, too, we can take one of those products, purify it, isolate it, drop it in some dichloromethane, put just a little hint of acid in there, or Lewis acid, some sort of metal cation, and heat it to 40 degrees, and we end up getting this product distribution. So that indicates to us that some carbocations must be forming. So what's happening in this reaction? This implies, for this reaction, that we heat it up and it breaks apart, forms the carbocation, and then when it collapses, it can collapse to form the product. So we have a way of going from the bromine in the 2 position to the bromine in the 4 position. Again, I'm using the 1,4 versus 1,2 addition. And we end up getting this equilibrium that goes through. We get an equilibrium because the carbon-bromine bond can break heterolytically, that is, it comes off as a bromide and forms a carbocation, and we get equilibrium there. So what's going on then at low temperatures? I want you to think about an energy profile. So what's happening? The first step in our reaction is proton transfer. The proton is going to go to the end of the system to form the more stable allylic cation. That allylic cation then can either at low temperatures, we find that we get more of this product. So this must have a lower barrier to get to, because at low temperatures the activation energy is lower and we get some of this. At high temperatures the activation energy is higher, so less of this has energy to get over that barrier and get to the 1,4 position. But notice that in the products this is lower in energy. We know that to be true. We know the more substituted alkenes are more stable than less substituted alkenes. So we talk about this as being kinetic versus thermodynamic control. Take a look at what's going on. At low temperatures, our reaction proceeds to give us the less thermodynamically favorable product. This thing cannot be in equilibrium conditions. It is kinetically controlled. Whichever has the lower activation energy will form more. Okay? Once we heat it up, if we go to higher temperatures, now all of a sudden, even though there is a kinetic preference to form this one, it can go back, and we're going back and forth, back and forth, back and forth. And under those conditions we reach equilibrium, and we're going to get more of the more stable compound under equilibrium conditions. So this is the important thing about kinetic versus thermodynamic control. If we're doing something under kinetic control, we're under non-equilibrium conditions. If we're doing a reaction that's under thermodynamic control, we're under conditions of equilibrium. That's a very important concept. It so happens that very often the kinetically favored product and the thermodynamically favored product are the same. That happens more often than not, actually. But every once in a while we get situations where they're different. The kinetically controlled product is not the same as the thermodynamically controlled product. And in those cases, we can get the kinetically preferred product by doing it at lower temperatures to get the kinetically preferred product. So why is that the case? Well, let's think about it. In some ways, it doesn't seem to make sense. You might think that this is more sterically hindered approach to hit this one than this one. And although that may be kind of true, it's not too bad. Remember, carbocations, this is a pi system and it's flat, and the nucleophile is going to approach from above or below the plane of the pi system. And to be sure, there is a little bit of steric hindrance from this methyl group over here that's spinning about. So approach from this side is hindered, but they're mostly going to be approaching from above or below that plane of the pi system. So there's not a lot of resistance for this particular system. If we think about it then, we know the transition state. We know this transition state must be lower in energy than this transition state because it is the kinetically favored product. And let's think a little bit about the transition state. What's happening in the transition state? We have a carbocation. In the transition state, negatively charged bromide is coming along and a bond is beginning to form. Just at the instant that the bond begins to form, our charge starts to collapse from being a positive and negative to a neutral compound. But in the transition state, we still have quite a bit of charge development on the carbon center. And a secondary like carbocation, because we're losing the resonance now. In the transition state, we're losing that delocalization of charge in the transition state because the bond is beginning to form. It's no longer delocalized. It's actually down here. This bromine isn't delocalized. It is attached to the 2 position. So in the transition state, we have a lot of charge development on this site, which is more stable because it's a secondary site than here, which is a primary site. So at this point, the carbocation stability loses the delocalization and is dependent on our traditional carbocation stability of non-delocalized systems. And a secondary carbocation is more stable than a primary carbocation. And that explains the differences in the transition state heights, the energy levels of the transition states. So the energy of the product is just a reflection of the relative stability of alkenes when we're under thermodynamic control, because this is a more stable alkene than this. Now you will notice a few times I've said I often put, let's get out of here. for just a second. I often put notes and things, and now in this one I put challenge. Extend this analysis and speculate why 1-bromo Z2-butane is only found as a very minor product. So this is the cis equivalent of this. It should be more stable than that. The cis isomer is more stable than that, but less stable than that, so it's somewhere in between. So why don't we get some of that? We get some of this. We see almost, it's a very minor amount, less than 1% of the cis product, and my challenge is for you guys to speculate on why that might be. Big hint there. So when you're going through the notes, look at the bottoms. The other things about the bottoms, if you're looking at the slide and you don't quite feel you have a grasp of it, I actually have a lot of links to the information that's on that slide. One of the reasons is because I steal the images from the internet, okay? So I sourced them. This tells you where I ripped off that image. So I'm giving the authors credit and also pointing you to a place that may give you more information if you're finding this ambiguous. So don't forget to take a look there. Okay, so this is just tells us a little bit more of this analysis about the carbocation resonance forms and then the energy level, the transition state, kind of what we just discussed. Okay, so how about the HCl addition to isoprene? Isoprene is the methyl substitute of butadiene. We can protonate this. We can protonate either end, right? We're probably not going to protonate, our proton is not going to go there or there. Why? If it goes there, our charge ends up on the end carbon and it cannot delocalize to stabilize itself. It would be a primary carbocation either way. So our proton is either going to go to this carbon or to this carbon. Let's take a look at the carbocations that form when we do the protonation so that we could predict the products. If we protonate at that end, we get this thing, which is a stabilized, delocalized system. Okay, it's an allylic carbocation. We know that's more stable than non-delocalized carbocations. We could protonate on the other side. Okay, and if we protonate on the other side, again, we're going to get an allylic carbocation. Let's take a look at these. Let's do a little bit of analysis. We have a primary carbocation versus a secondary carbocation, and the true structure somewhere in between. Okay, so that's going to be more stable than just an allylic radical, where, well, actually, I'm sorry, it's the same as an allylic radical from 1,3-butadiene. But in this one, we protonate. We have our primary resonance contributor and our tertiary carbocationic resonance contributor. So this is a very stable resonance contributor. This is going to contribute the most to the true structure of this compound, and this is going to contribute the most to the true structure of this compound. But this should be more stable, right, because it's tertiary. So this carbocation is more stable than the one above it because we have more tertiary carbocationic character.
So where does the double bond transfer from the top middle one to the top right one?
The top.
Top middle. Top.
If we just push our electrons there.
Above that. Yeah, how does that transfer to the right one?
Oh, I'm sorry. There should be a double bond there. Okay, so I made a mistake. I do it. I make mistakes. So if you're drawing it, go ahead and draw the carbon-carbon double bond. I'll fix that after before I post them. Okay, so where do our products come from? This is a much more stable carbocation than this. And remember, when we do these protonation reactions, we tend to protonate and get the more stable carbocation. So we don't get a lot of chemistry occurring through the pathway on top. Most of our chemistry comes from the pathway at the bottom. To be sure, we will get very minor amounts of product here, But we will get these two products because this is the carbocation. And we can get varying amounts by changing the temperature because we still do have a kinetically controlled versus a thermodynamically controlled product. This is the more substituted alkene, and this is the less substituted alkene. Okay, so now we're going to look at another reaction. This is a new reaction that you guys haven't seen before. And when I write it like this, the first thing that's probably going through your minds is, what the heck is going on, right? What's going on here? And also, we haven't been doing radical chemistry. We recognize that it's out there. But most of the reactions we do in organic chemistry involve a nucleophile and an electrophile. Is there a nucleophile here? Is there an electrophile? Or is it a radical mechanism? Maybe this is a trick that you'll find some people like to do. They'll give you that reaction in a test. But if we draw it like this, it's a lot easier to remember this reaction. And typically, we're going to be used to seeing it drawn on the board like this. Okay? And as soon as we draw it like this, we don't recognize it. We don't see the reaction. As soon as we draw it like this, as soon as we place it in the way that it's going to go, and we can even think about pushing our arrows. Okay? So this is a lot easier to see the reaction that occurs. This is called the Diels-Alder reaction. And what kind of reaction? The mechanistic features. It's a concerted mechanism. We'll talk about that in just a second. Cycloaddition. That's because we're doing an addition reaction and forming a cyclic structure. It comes from a bunch of reactions that are known as pericyclic reactions, which are reactions that go through concerted mechanisms with a cyclic transition state of a conjugated pi system. Okay? There's a whole bunch of reactions that are pericyclic reactions. We're going to look at just one here. This reaction, there's been many, many, many PhD theses written about it. And let's just think about why that might be. As organic chemists, we like to form carbon-carbon bonds. Look at this. We're forming two carbon-carbon bonds here, right? And we're making a six-membered ring. How many drug molecules, if you take a look at them, have six-membered rings in them? A lot of them, okay? So this is very powerful synthetically. We can form two carbon-carbon bonds. We can form a cyclic structure. And you'll find out in a little bit there's stereochemical consequences as well. Let's take a closer look at the reaction, okay? How does this reaction occur? Well, it occurs through what we call a cyclic transition state, and it's concerted. There are no intermediates on going from here to here. There's just, we learned that in first year, there's just one step. We go through activated complex to the products. That's what we mean when we talk about it being concerted. The bonds are breaking and forming simultaneously in the transition state. Now, we want to be a little bit careful here. It's not going to matter for you guys, but for those of you that go on in chemistry, the bonds are breaking and forming simultaneously. That doesn't necessarily mean that they're forming to the same extent. Once we get substitution in here in the transition state, this bond, if we had substituents here, might be much more formed in the transition state than this bond might be. Okay, so that can happen. Just for when you get in later years, understand that that can happen. As well, I want you to note that the dienophile approaches from below or above the plane. We talk about a diene. This is our diene, and this thing loves to react with diene, so we call it a dienophile. And that's the nomenclature you'll find for these Diels-Alder reactions. We have a diene and a dienophile. Okay? And we want to remember that they approach each other like this. Okay? They're not approaching each other like this. It's like this, or like this. The other thing that's interesting about these is that reactions are governed by homo-LUMO orbital interactions. We did some analysis already about homos and LUMOs. So we can think of them as one being a nucleophile, and that's the one where the highest molecular orbital is going to seek out an empty spot to throw its electrons. That's the lowest unoccupied molecular orbital in the other reactant. We have to have symmetry match up when that occurs. The lobes have to match up in phase in order for the electrons to go from here. This is the HOMO of our diene, and it's going to donate its electrons into the empty LUMO here. And in order to do that, the orbitals have to match up and be in phase of where the bonds form. Okay, you'll analyze these to death in Lukeman's physical organic course in your third or fourth year. It's known as the Diels-Alder reaction. Diels and Alder won a Nobel Prize for this. They found it in 1928. They won the Nobel Prize in 1950. Typically, when we do these reactions, we have electron withdrawing groups, and that's what these carbonyl groups are, attached to what we call the dienophile. That's the alkene. We often, although we don't hear, this is the original, the first reaction that they discovered, we often have electron donating groups attached to the diene. And that actually facilitates the reaction. If we don't have those things, the reactions go much slower. If we have an electron donating group on the diene and an electron withdrawing group on the dienophile, the reactions go faster. We can also have what we call inverse demand Diels-Alder reactions, where we flip that. We put the electron withdrawing group on the diene and the electron donating group on the dienophile. Those also go too, although they're less common. So remember, we did this conformational analysis of butane, where we have these different conformations, and this is the highest energy conformation, and it actually doesn't exist very long. It's kind of like a transition state because of the steric interactions between those methyl groups. Whenever we have eclipsed, here our hydrogen and methyl group are having steric problems getting past each other. The most stable conformation is down here, where the two methyl groups are away from each other, and that's indicated here. This is the most favorable conformation. Well, we can have the same thing happen with butadiene, only it's slightly different. One of the things, here's the most stable conformation of butadiene, everything in a plane, and the reason is because all of the p orbitals line up. And remember, we talk about it not contributing a lot, but one of the resonance structures we can draw has a carbon-carbon double bond in the middle. So there is a bit of a barrier to rotation there about that middle bond. So our system, our diene system, if we're looking down here, we can have one out this way and one this way. That would be what we call our S-trans conformation. We talk about the S, it's trans about the sigma bond. Okay? We can also have an S-cis conformation of butadiene. Now it's a cis conformation about that sigma bond. That's what S-trans and S-cis stands for. The S-trans is much more stable than the S-cis, and this is actually a lie. The S-cis is actually not the most stable conformation on this side of things. It's actually a little bit twisted, just a little bit, and we get a little bit of a gauche. That's actually the most stable conformation, but it's close. It's very close to the completely cis system because there is some favorable orbital overlap between those p orbitals, and that's being shown here. Okay, so in order for it to react, it has to be in this. This is the reactive conformation of our butadiene for a Diels-Alder reaction. If it's in this conformation, it can't react because the bonds can't form, right? This is too far away. If we take a look back at the transition state, right? We're forming a bond between that carbon and that carbon, and that carbon and that carbon. If this were way back here, it would be too far away to form a bond. So it has to be in the S-cis conformation. So this is the reactive conformation. As it turns out then, as soon as we start throwing substituents on, we change the reactivity of butadiene. If we put one lonely methyl group on, it actually becomes more reactive because this is a favored conformation and the trans is less favored. If we put two methyl groups on there, the S-cis trans conformation becomes very unfavorable because we're starting to bulk up the steric bulk here. The reaction can still go, but it goes 1,000 times slower than this reaction. Okay? So in order to make it go, we might have to heat it up, something like that in the lab. Or it may be that this reaction happens in few seconds and this reaction takes few 10,000ths of seconds, which we can still do. Okay? As soon as we put two T-butyl groups on here, this thing becomes completely unreactive, because then these things are so bulky that we cannot even achieve an S-cis conformation when we have it bulked up. Now, if we take a look at this, we've actually clipped together and we've made it so it can't get into the S-trans conformation. It's stuck in the S-cis transformation. And as it turns out, this is a very reactive dienophile. I'm sorry, a very reactive diene in Diels-Alder reactions, because it's stuck in the S-cis conformation. That thing is so good at being a dienophile, it reacts with itself, it dimerizes, and this is, when you buy this stuff, you buy it in this form. When you want to use this, you actually have to heat it up, and you just throw it in a flask. This is a liquid, you throw it in a flask, heat it up, and it distills off the monomer. Okay, so you crack the diene to get the monomer in the lab. It's really easy to do, and then that will last for a little while, but it'll eventually just dimerize back if you don't use it right away. That reaction happens hours long. So you have a long time. Once you distill it, you still have lots of time to do the reaction that you need to do. Here's just showing some more. So remember, this is the reactive conformation. This compound is 5 times more reactive than this conformation. That must be a very difficult experiment. I don't know how they did it. This compound is actually very reactive because this is a favored conformation, because for this to be in the S-trans, you get interactions between here and the T-butyl group. So that one's actually favored. This one's not favored at all, because in fact, although this is conjugated, the two systems actually turn out to act like isolated alkenes because they're not in the same plane. This is just showing the reactivity. Here's our butadiene itself. Look at this. Look at this cyclopentadiene. It is 1,350 times more reactive than butadiene itself, because we've restrained it into the S-cis conformation. Same with this system. This one doesn't really have the opportunity to get in the S-trans conformation, so it's quite reactive as well. When we put substitutions, we affect the HOMO and LUMO energies. If we put electron donors onto an alkene, we raise all of we lower all of the, what do we have? No, we raise all of the energy levels. I see where I was. So the HOMO goes up, the LUMO goes up in terms of its relative energy level when we put an electron donating group onto that pi system. If we put an electron withdrawing group onto the pi system, we lower all of the energy levels. What we require when we do a reaction, remember, just like when we talk about Lewis structures and all that, so here's a reaction. We can think of this as being our electrophile. It has an electron withdrawing group on it. We didn't do anything to the butadiene, but it's our nucleophile. The electrons in this HOMO are going to reorganize and go into the LUMO of this reaction. And the reason that it works is that the energy levels, these are the orbitals that have to interact, and they have to be close in energy. When we put electron withdrawing group on that, we lower this energy level down a little bit, and we get better energetic overlap between these two systems, okay? So that facilitates in the bonding. Just like when we talk about the reason that carbon and oxygen form nice pi systems, and this is a good resonance structure. When we have something like this, CH3, OH plus OCH3. We can draw a resonance structure. And that's because we have 2p overlap. And this is a strong contributor. In fact, we talk about this being a very good contributor because we could draw an octet of electrons around it. But if we have something like this, this is a poor contributor because we have 3p and 2p overlap, and the 3p is much higher in energy than the 2p, so we have poor energetic overlap. The same thing happens here. If we can lower this so that it has better energetic alignment with the nucleophile, we get stronger interaction and the bond begins to develop. Now, on the other side of things, we also have to have this interaction, but we don't get concerned even though we're making it higher. This starts the bond, the bonds forming. Okay, so you could imagine if we put electron donating groups on here, we're going to push this up, and then we get even better orbital overlap. So the other thing that's nice about the Diels-Alder reaction is that it happens to be stereospecific, stereoselective, and regioselective all in one reaction, okay? This guy's amazed by that. His mother just told him about the Diels-Alder reaction. Okay, what do we mean by stereospecific, stereoselective, and regioselective? Okay, stereospecific means, if you take a look at the Diels-Alder reaction, it means there is at least one stereocenter, maybe more, that you get only one possible isomer. So if you have, we'll see in a second, there's a component of the reaction that's stereospecific. There's another component of the reaction which gives us some stereoselectivity. Stereoselectivity means that we have the possibility of more than one stereoisomer and we'll get one over the other. Stereospecific means we have the possibility of more than one stereoisomer and we'll get only one over the other. Regioselectivity just talks about where the bonds form. So let's take a closer look at stereoselectivity, specificity, and regioselectivity. Okay, so here's an example of the stereospecific part of a Diels-Alder reaction. The geometry of the diene, if we have a cis geometry in our dienophile, that will be retained in the product. Okay, so that's why it's specific. The same here, whatever geometry we have here gets retained in the product. Okay, so this is cis here, and it remains cis relative to its component over there. The same with all of the relative stereochemistries here. That's where it's stereospecific. Where we get stereospecificity is this can approach where they're sticking out, in which case we get what we call the endo product. We call it endo because these are kind of below the ring system. Okay, so we call that endo. The other isomer we could get is the exo product, okay? And we get much more of the endo product than the exo product. So if we think about it, right away we can't think of a reason for that. And in fact, we might think that this should be favored because the way this forms, this pi system has to be underneath here when it forms. We'll get a look at that probably on Friday. So it's stereoselective as well. And in this instance, actually, interestingly enough, what's going on here, how do we get this? This would indicate what's really happening is when we heat this up, this is probably undergoing cis-trans isomerization, and it's that isomerized compound that's reacting with the dienophile to give this compound where we have those in a different. If this is our dienophile, we get only one product. Okay, I just have one more slide. Sorry that I'm going a little bit over. Regioselectivity. You can imagine that this can react like this, or we could flip it over and it could react like this. We actually get more favorable. We get 6.7 times more of this product than this product. So we talk about it being regioselective because the bonds are forming in these regions. If we flip it over, we get the other regioisomer. Okay? And these are very regioselective. So the reaction is very good for building stereochemistry into products. And we're going to stop there. We have a little bit more to do here, but you should have enough to finish your